the refracting surface curves inwardly, and we have two biconcave lens. Now we have another one with only one refracting surface, okay, which we call as plano. So when you hear plano concave, let me talk about plano convex first. So a plano convex lens only has one refracting surface. So this is plano convex. Then we have plano concave. Plano concave, yes, it is curved inwardly with only one refracting surface. So if you see the one-sided, they are plano. The double refracting surfaces are all biconcave, biconvex, and so on and so forth. Then we have another type we call as concave and convex meniscus. This one looks like the meniscus of water. So convex meniscus, okay. Here we expect to see convex, the refracting surface curving in, okay, and then so this is the refracting surface. Then the back is curved like the convex, the meniscus of water, okay. Then the concave meniscus, where we are interested in, curves. Oh, sorry, this is here. This must be convex meniscus. Then if we draw it in the same way and then change the refracting surface, we have concave meniscus. Meaning in this one, we are interested in this side. In this particular one, we are interested in the part which curves inwardly. So these are the meniscus thing. Okay, so basically these are the types of lenses. Please, are we okay?
Mr. Adria,
Hello.
please, can you go over the definition for the convex meniscus?
The convex meniscus. You see, where the arrow is represents the refracting surface. Okay, so the convex meniscus, the convex lenses curves outwardly. So this is the refracting surface curves outwardly, but this is the other side. So the arrow represents where the refracting surface is. Are you okay?
Yes, please.
All right. Can I clean the board, or you are writing?
Please, you're writing.
Please hurry up. Can I continue?
Yes, please.
Okay, so let us look at convex. Convex lenses are known as converging lenses. Why converging? They are converging lenses because when beam of light is incidented on convex lens, hereby convex lens, the lens has the ability to converge the parallel beam. So when I incident light parallel rays at one end, okay, when the ray of light is perpendicular to or hits the center of the lens, which is the optical center, it goes undeviated. Later on, you see this one. But when it is not hitting the optical center, it will refract. But the refraction will be said that it will be converged at a point behind the mirror. Okay, so if you incident a lot of rays, they will all converge at a point behind the mirror, the lens. Okay, so that is why convex lenses are called converging lens, because they bring together they bring parallel rays at a common point along on the principal axis. Please, this is what I have in my hand is an example of, this is a biconvex lens. Biconvex lens. It is common in the lab. Okay, so if you haven't seen a lens before, this is one excursion. Then, so that's why convex lenses are also converging lenses. Then let's look at its other counterparts, concave. When ray of light passes through the optical center, it goes undeviated. But when the ray doesn't hit the center, this one has the ability to diverge. So this one will spread the parallel rays hitting it. So this ray would spread out, they are parallel. So this will also spread out. This will spread out, and they always spread out in a manner which appears as if they are being diverted. This diverted rays appears to be diverted from a common point. So they always appear to be diverted from a common point at the other side of the mirror. And this point where diverted rays appear to be diverted from is the principal focus, F. So this is the reason why concave lens is also known as diverging lens. So convex or converging lens and concave or diverging lens. Are we okay?
Yes, please.
All right. Then let's look at parts of the spherical or our parts of the optical lens. This is similar to what we've done under mirrors. So I'm sure we'll just go through this, cruise through this quickly. Now, please, uses. Let's look at uses of these things. Okay, or I will skip this and want you to read on the uses of the lenses, convex, concave, and the plano. Okay, a quick usage of this is that this is used in microscopes. You are a biology student. The microscopes you use in the lab, okay, their ability to magnify and all that is as a result of a combination of a number of these convex lenses. So this is used in microscopes. This is used in telescope. It is also used in correcting eye defect. Your glasses, give a student your glasses, okay? And then I want you to get more, okay? Get more information on the usage of the convex and then the concave lenses and then the plano and then the meniscus, okay? Please take note of that as an assignment which you have to read and then make notes for me so we can move on. Is that okay?
Yes, please.
Yes, please.
Okay. Let me check roll call. Okay. I think attendance is encouraging. Nana Devua. Oh, she's not here.
Data, please, I'm here.
Ah, okay. All right. Let's. Hey, Travina, you are really trying. Where is Isra? Isra, are you here?
Yes, please.
Hey, okay. Isra, Isra. Okay, so types of the optical parts of the optical lens. So, you see, let's look at the mirror and then discuss it as well. Brittany Asante, are you here? Asari, rather. Are you here?
Data, she's not here.
AB this is AB is the aperture. AB is known as the aperture of the mirror. A mirror has just a small aperture. So you don't draw a mirror like there's a giant, no. It's not like that. The mirrors we use in the lab are very, very small, meaning they have very small aperture. In the same way, for lenses, lenses also have a very small aperture. So if this is AB, then AB is also the aperture of the lens. Okay, very small. Look at this lens I just showed you. Very, very, very small. Okay, so from down up is the aperture of this lens. Then for mirror, the point P, where the line, the horizontal line, the principal axis divides the mirror into two equal parts. This we call as the pole of the mirror. When it comes to lenses, the center, which the optical, the principal axis divides, is known as the optical center, C. So C is the optical center. So for mirrors, under mirrors, it is the pole. For lenses, it's the optical center. Now a line which divides the lens into two equal parts, okay, is a principal axis. So this horizontal line, which in mirrors passes through the pole, here passing through this optical center, is known as the principal axis. So let me, OP. The line OP is the principal axis. Okay, so similar, so similar to mirrors. So let me clear the mirror and only talk about.
Oh, Mr. Dear.
You can draw. You can draw, okay? If you are enjoying mirror, you can still draw.
Oh, Mr. Dear.
Oh, Irene. Okay, so OP is it. Now, lines, rays that are parallel and close to the principal axis. Rays that are parallel and close to the principal axis, which we call as paraaxial rays. Okay, please, lenses refract, mirrors reflect. So there is a point on the principal axis where rays that are close and parallel to the principal axis after refraction actually converge for convex lenses. So when the ray is close and parallel to the principal axis OP, after refraction, they all converge at a point on the other side of the lens. That point where paraaxial rays converge after refraction is what we call as the principal focus or the focal point. For lenses, for biconvex lens, because a biconvex lens has two refracting surfaces, this side and this side, there are two principal foci or two focal points, one at this side F1 and another at this side F2. Because light, let me draw another one. Irene, I'm drawing another one for you, okay? So if this is C, it means that the light, incident light is coming from left to right. It can be from right to left. So if it is from right to left, then after refraction, they will all converge at a point at the other side. Okay, so if it's from here, then F2. So when you draw a convex lens, there are always two, we have two principal foci, F1 and F2. So a point where paraaxial rays actually converge after refraction is the principal focus or the focal point. When it comes to the other one, which is convex, this is how it looks like.
Mr. Dear, do you mean concave?
This is, yes, I mean concave. Okay, for concave, when paraaxial rays hit it, it diverges. But the divergence always the refracted rays or the diverted rays always appear to be diverted from a point over here. So F1. So this one too, because there are two refracting surfaces, this one also okay, has two principal foci over here or at the other side. Okay, so the principal focus or foci of a lens, okay, is a point on the principal axis where paraxial rays converge or appear to be diverted from after refraction. Here I'm combining the principal focus of convex and concave lenses. It is a point on the principal axis where paraxial rays, Akofala,
Mr. Dia, please, does it mean that the principal focus of the biconcave lens is virtual?
Biconcave, yes, it's virtual because the diverted rays appear to be diverted from the point. And this one, its principal foci, it's real. So you are right. Okay.
Thank you.
All right. So it is the point on the principal a point on the principal axis where paraxial rays converge or appear to be diverted from after refraction. And with this, I'm combining for the principal focus for both of the lenses. Are we okay?
Mr. Dia, please, you said where the paraxial rays converge
Actually
or appear
converge.
to be diverted.
Okay, so the principal focus or please the focal point, okay, of a lens, and of a lens I'm combining of a lens is a point on the principal axis where paraxial rays actually converge or appear to be diverted from after, you can add after refraction. So with this, I've combined the principal focus for all the lenses, okay? And because of this, as Akofala said, convex lenses have a real principal focus, and then concave lens has a virtual principal focus, okay? Here we also have the center of curvature, and as we saw on a lens mirror, the center of curvature is a point on the principal axis where rays that incident on the lens perpendicularly, okay, pass or converge after refraction. Okay, so there is this similarity lenses also has with mirrors. When you understand the details of the mirrors, you can apply it to this one as well. Are we fine? Are we okay?
Yes, please.
We saw, so there's a C over here, because we are talking about biconcave, biconvex. There are also two center of curvature. one at this side and one at the other side, just as we have for the principal focus or full side. Okay, so one center of curvature here, another one. The only difference is that for lenses, we try to distinguish it a little bit from mirror. So in mirrors, we represent the center of curvature by C, but when you come to lenses, this is F, and this is 2F. This is F, and this is another 2F. Just a slight modification. The point is that when you forget and instead of 2F, you write it as F, you won't be penalized because it isn't any profound thing. What's important is that by virtue of this having two refracting surfaces, one is here, one is there, on and on and on. All right. Still, we have the distance between the optical center. The distance between the optical center, C, and the principal focus is the focal length, F. Okay, then the distance between the optical center to where the center of curvature is, 2F, is still radius of curvature, R. The relationship R has with F, the value is still the same. R is equal to 2F. It hasn't changed. Please, are we okay?
Mr. Please, what's the R for?
R is the radius of curvature. R is equal to the radius of curvature.